Hello everybody, welcome to this 5th lecture session of the course Database Management Systems. Before we start our today's discussion, let us revisit the steps that are involved in database design. If we look at the phases or steps involved in database design, and we will be developing a database to represent the data contained in a mini world like institutional database, company database or so on and so forth. So, this is the mini world. For whatever mini world we wish to develop the database or design the database, first the requirements collection or analysis step will take place. In this phase, we try to understand the requirements of the end user and the data that is available that need to be captured into the database and that is available in the mini world, that we will understand, and the result is a data requirements document. Once the data requirements is available, then we will perform conceptual database design either using ER modeling technique or EML technique, whatever it is. And we here it is a high level data model. We design the database using high level data model that gives a overall picture about the data that is going to be captured into the database, a high level description about the data that will be captured in the database. The result is a conceptual schema in high level data model, that is ER model or EML model, and up to this phase it is independent of any database management system. And then once we are ready with the conceptual schema, that is for example ER diagram what we have seen in the previous class, then we need to carefully translate that into a data model or a logical schema that is very specific to the database management system we have chosen. And this process or this step is called as logical database design, where we take up the mapping of the conceptual schema into logical conceptual schema, that is the conceptual schema which is specific to the database management system. This is called as mapping, and up to this it is independent of the DBMS. And once we are done with the conceptual schema using ER diagrams or EML, then we need to decide upon what implementation of the database management system we are going to use, and it could be either RDBMS or it could be ODBMS or ORDBMS, network model, so on and so forth. There are so many data models available which are specific to the implementation. We need to choose one among them, and let us assume that we have chosen to go with the relational database management system. So that is why the whatever conceptual schema we have designed in the previous phase, we need to carefully map that into a conceptual schema which is specific or which is supported by the specific database management system. In our case it is going to be relational database management system, and now this is called as the logical database design. Once we are done with the logical database design, and then if it is relational data model, and the database schema consists of a collection of relational schemas, and where each relational schema is going to describe the structure of a relation. The relation consists of a relation schema and a relation instance. Okay, so from now onwards we will use the terms relational instance and then relation interchangeably. So relation will contain tuples, and wherein each tuple or each row of the relation, which we see it as a table, the relation. So each row or a tuple will obey the structure that has been specified in the schema for the relation. Okay, and then once we are done with that, we will be doing schema refinement in between, and then finally we will go for the physical database design. Now in this class, the subject of today's discussion is we are going to talk about this step, that is logical database design, where we map the conceptual schema in terms of high level data modeling is mapped into conceptual schema in terms of the data model that is specific to the database management system. In our case it is relational data model. Okay, today's discussion is, the content is, first we will see the mapping regular entities, that is let us understand that we are given the high level data model or the high level conceptual schema which is in terms of ER model or ER diagram is given to us. Now our job is to perform logical database design, that is mapping that ER schema into the relational database schema. First we will see how to map the regular entities that we see in ER diagram into the tables or relations, then mapping weak entities, then mapping relationships, that is one to one relationship, one to n relationship, n to m relationship, and then we will see how to map the multi-valued attributes, then how to map n-array relationships, and then we will also discuss how to map the class hierarchies. and if there is superclassing and subclassing kind of relationship in ER diagrams, that is captured in ER diagrams, how to map those things, those concepts into the relations or tables, that we will discuss in this class. Okay, first let us have a look at how to map the regular entities. If you look at the ER diagram, we will have some entities which are called as regular entities, and we have some entity types which are called as weak entities. All those entity types which have unique identification, that is which have a attribute which acts like a key which provides us unique identification of entities in the entity set, are called as regular entities. Okay, now we will see how to map such regular entity types into relational schemas. The rule says like this: for each regular entity type E in the ER schema, that is ER diagram, create a relation R that includes all simple attributes of E. Suppose if I have something like this E, and which has some attributes, simple attributes A, B and C, something like this, and then which has some complex attribute X which contains P and Q as subcomponents, then what I should do? Create a relation or relation schema R for this regular entity type E and include all the regular entities. One among them is going to be a key. So include all regular attributes as attributes of the or fields of the relation R. So that's why you will have A, B and C. That is the first step. Then choose one of the key attributes of E as the primary key, and in this case A is going to be the primary key. So I underline that. And then if the chosen key of E is a composite, the set of simple attributes that form it will become together will become the primary key. Of course, in this case it is not there, and at the same time, if the entity type, that is a regular entity type, has some composite attribute or complex attribute which contains subcomponents, then how to capture that? In this case, X is a complex attribute which internally contains P and Q as the subcomponents. Then those subcomponents of the complex attribute can be modeled or captured as simple attributes for the relation R. So that's why I will have P and then Q. Now this regular entity type has been mapped into relation schema. This is how we map regular entity type into a relation schema. For example, let us have a look at this. Employee has employee ID, name and then age. Let us assume that this entity type, regular entity type, is part of our ER diagram. Then there is a complex attribute address which contains house number, street, city and then zip code. Then how to map this? According to this, I create a corresponding relation for the strong or regular entity type and then make all simple attributes as the attributes of the relation: employee ID, name and age, and choose one among them, one of the attributes as the primary key. In this case, employee ID is the primary key, and then as far as the complex attribute is concerned, I will pick up all the subcomponents of the complex attribute and then make them as attributes of the relation. So house number, street, city and then zip code will become the regular attributes of the relation EMP. So this is how we can map this into a regular entity type into a relation schema. Next, we will see how to map weak entity types. The rule says that for each weak entity type W in ER diagram with owner entity type E, that is every weak entity, we have understood that every weak entity will also have its owner entity. Suppose if you look at the dependent weak entity, the owner entity type is the employee, because every dependent is attached or associated with one or the other employee. Then create a relation R and include all simple attributes of W, that is weak entity type, as attributes of R. And also, that is, we know that since we need to provide or identify some attribute as the primary key, and then we understand that for weak entities we don't have primary keys, and the unique identification for the entity in the entities in the weak entity type will only available in conjunction with the owner entity type. That's why we need to include as foreign key attributes of R the primary key attribute of the relation the owner entity that corresponds to the owner entity type S. The primary key of R is the combination of the primary keys of the owner entity and the weak entity, that is the partial key which is part of the weak entity, and this is how we can map the weak entity type into a relation schema. For example, now let us assume that we have a relationship between employee regular entity and then dependent weak entity. And dependent weak entity has attributes like dependent name, age, and then relationship with the employee. Then the employee regular entity has the attributes given here, name, employee ID, age, so on and so forth. And this regular entity, we have mapped this into the relation which is shown here, and then how to capture this, how to map this weak entity dependent. Now what we will do is, we create a relation called dependent and we attach all the attributes that are part of the weak entity as attributes of this relation, fields of this relation. So dname is there, age is there, and then relationship. At the same time, we also include the primary key of the owner entity. Who is the owner entity here? Employee is the owner entity type. So primary key of the owner entity type is employee ID. So we include the primary key of the owner entity type as foreign key in this relation. Now the combination of the employee ID, which is a foreign key here, and the department name, sorry, dependent name, this put together is going to act like the primary key that is given here. And the attribute which is taking part in becoming primary key for this weak entity type is called as the partial key, and that we have seen in our previous discussion when we learnt how to represent weak entities in while drawing ER diagrams. This is how we can map the weak entity types into relations. Now we will see how to map the relationships into the relationships of ER diagram into relation schemas. First we will see how to map one-to-one relationships. For each binary 1:1 relationship R in the ER diagram, identify the relations S and T that correspond to the entity types participating in the R. Now there are three approaches available. First is called as foreign key approach, second is called as merged relation approach, and third one is called as cross reference or relationship relation approach. Now let us try to understand the concepts behind these in terms of a valid example. First one is mapping binary 1:1 relationship using approach 1, that is foreign key approach. Let us assume that we have employee entity type and then department entity type, and employee entity type has employee ID, age and name as the regular attributes, and the department has department ID, department name, and then location as the regular entities. Because it is a one-to-one relationship, binary relationship. What is a binary relationship? If the number of types of entities that are involved in the relationship is 2, it is called as binary. If it is only 1, it is called as unary. If it is 3, it is ternary. If it is more than that, it is called as n-ary. That is called as the degree. This is called as the degree of the relationship, and this is called as the cardinality of the relationship. We have 1-to-1 cardinality, 1-to-n, and then n-to-m cardinality. And in this case, specifically we are going to discuss about how to map 1-to-1 binary relationships into the relation schemas. Now we have employee and then department. Because it is a regular entity, I assume that I have created or I have mapped this into a relation called employee with employee ID as the primary key, and then other two simple attributes have been added here as fields. Then since this is a regular entity type, this is also mapped into a relation where DID is the primary key, DName, and then DLocation. What is one-to-one relation? How to read it? I need to write one here on one side and then one on the other side. I can read it from this side or I can read it from this side. If I am reading it from left to right, each employee can work with only one department. That is the meaning. And if I am reading it from this side, sorry, this is a not works with managers relationship. Each employee can manage only one department. And if I am reading it from right to left, each department is managed by only one employee. But if you look at the participation, let us assume that if there are 1000 employees and then only 5 departments, only 5 employees can become managers, and remaining all 995, they are not managers. That is why the participation of employee entity type in this relationship is going to be partial. That is why it is indicated using a single line which is joining this entity type rectangle with the diamond. And if you look at the department entity type, its involvement is going to be total, because there are 5 departments in our example, and each department must have at least one manager and then maximum one manager. So that is why its participation is going to be total. That is why it has been indicated using a double line. Now if it is a foreign key approach, what I can do is I can include the department number which indicates the employee is managing which department as an attribute and which is a foreign key in this employee table. But that is not correct, because only 5, if I assume that there are 1000 employees, only 5 of them can become managers, and then remaining 995 employees are not managers. So if there are 1000 employees, how many rows will be there in this table? There will be 1000 rows, and for only 5 rows there will be some valid value under this particular column, and then for remaining 995 columns rows I will be wasting space. So that's why this is not an elegant approach. The other possibility is I can include the manager SSN, that is which is a foreign key here in this department table, which refers to the employee ID who is the manager of that particular department. Does it work? Yes, it is perfect, because I know that it is a one-to-one relationship, and then the participation of department entity type is total in this relationship. That's why every department will have one manager and then maximum one manager, and it must have a manager. So that's why I include an attribute which is a foreign key and then which refers to the primary key of the employee table, and then I can give it some name. I am calling it as MGR SSN or MGR ID, which is a attribute name and which is a foreign key, points to the employee table or relation. This is the first approach, which is called as a foreign key approach. Now let us have a look at the second approach, which is called as the merged relation approach. In this approach, let us have a look at, that is, this is useful, the first approach, foreign key approach, is useful when it is one-to-one relationship, and then when the participation of one of the entity types is total and the participation of the other one is partial, and then you add a foreign key in the relation which indicates or which represents the strong entity type which is at the total participation side, and then include a foreign key which points to the primary key of the other relation. And in the other case, this is also a one-to-one relationship. Let us assume a scenario, we have countries and then capitals. Let us assume that capital names are unique and then country names are also unique. Now the country is a entity type, strong entity type. It has country name, population, and then president's name, and then capital has capital name and then capital's population. Now since they are regular entities, we can map them into relations like what we have seen in the previous discussion. Now what is the meaning of this? Every country will have only one capital, and every capital is associated with only one country, and then the rule says that every country must have at least one capital and then maximum one capital, and each capital city is associated with only one country and then maximum one country. That's why the cardinality is 1:1 and the participation is both sides, it is going to be double line. So if such is the case, in the binary relationship, if we see such kind of situation, then we can use this merged relation approach, meaning that there is a clear one-to-one correspondence between the entities in the country entity type and then capital entity type. So that's why instead of having two different relations for country and capital, then we can have a combined relation or table called as country underscore capital or something like that, and then we can merge them together. Here the country name, the capital city name, the population of the country, president of the country, and then population of the capital. Since the one-to-one correspondence is there between the entities in these two types, that's why I am able to merge both of them, and then it is also known that the participation of both the entity types in this relationship is going to be complete or total. So that's why I, instead of going for two different relations or relation schemas or tables, I have created only one relation schema, that is a table, and then I have merged, I have put all the attributes of these independent entity types together to form one single relation schema. This is called as the merged relation approach. The third approach is cross-reference approach or relationship relation approach. In this case, let us take the example of the previous approach, that is the second approach, is suitable when both the participating entity types are involved in a relationship totally, then it is advised. Then if we have this example, I have faculty entity type and then department entity type, and then faculty has faculty ID which is a primary key, and then key, and then faculty name designation. In department I have department number, which is a key, and then department name, and then location. If you carefully observe, it is one-to-one binary relationship only. Every faculty can become, the relationship is going to be HOD. That is, every faculty can become HOD of only one department, and then every department will have at least one faculty, and it will have only one faculty as the HOD. And then further it says that not all faculty members are HODs, and then some departments can be there which are not having HODs. So that's why if you look at the lines which are joining these rectangles with the diamond, they are single lines, meaning that what? The participation of these entity types in this relationship is going to be partial. So that's why they are single lines. That means some departments can be there which does not have any does not have a HOD, and then some faculty members are there who are not HODs for any department. So in that case, what should we do? We can adopt this approach wherein this faculty regular entity type is mapped into this relation schema, and then department entity type is mapped into this relation schema, and their attributes will become the fields for this relation schema. And then to capture the relationship, who is heading, which faculty member is heading which department, I can have a separate relation schema or a table, I call it as HOD, and then wherein I have two fields, faculty ID and then department, and this department is a foreign key pointing to department number of the department table, and then FID is a foreign key pointing to FID of the faculty table. I cannot add foreign key because it is one-to-one. I cannot add a foreign key here, the department he is managing, HOD. It is not possible because only few of the faculty members are HODs in fact. And then similarly, I cannot add the faculty ID which indicates the HOD of this particular department, because some departments may be there which are not having any HOD. So that's why it is better to capture this relationship as a separate relation called HOD, and then I include the primary keys and primary keys of both the entity types which will reference or which will refer to the primary keys of the corresponding tables. This is the third approach to capture the binary 1:1 relationships. Okay, now let us have a look at how to map the binary 1:1 relationship types. Let us try to understand this concept with another example. Mapping 1:1 relationship between two entity types. In this example, I have department entity type and then employee entity type. Okay, and it is works for. Let us assume that it is a works for relationship, and it is 1 to n, 1 on the department side, n on the employee side. I can read it from this direction, I can read it from this direction. If I am reading it from left to right, I should read it as each department entity can have association with n number of employees. That means it can have n number of employees can work for a given department. And if I am reading it from right to left, it says that each employee can work with only one department. And since it is single lines, it says that some departments may not have any employees, and then some employees may not be working for any department. That is the meaning of this representation. It is a single line, so it is not total. Some departments may not have any employees, some employees may not be working with any department. In such case, how to map this to relational schema? Since it is a regular entity type, map this into a relation, and since this is a regular entity type, map this into a relation, and include department number and then dname, which are the regular attributes of this relationship, entity type, as fields of this table. Then for employee table, employee ID, employee name, age, they become the regular entities, attributes. Then I know that for each employee will have only one department, so that's why I will include the department number here as an attribute in employee table, and which will refer to the department number of the department table, which is a foreign key, and then there is a specific attribute attached with or associated with this relationship. It also indicates that since when the given employee is working for a given department. So that specific attributes which is attached to the relationship can be captured as a field for the employee relationship, employee table or employee relation schema. And of course, in this case this is more suitable when the participation is like this, that is when every employee is working for at least one department, the min max is 1 comma 1, meaning that what, every employee works with only one department, maximum one department, and then it is, let us assume that it is 1 comma or 6 comma n, meaning that what, every department has minimum 6 employees and maximum any number of employees. So in this case this is going to be, and this is a total participation and this works fine. And if it is partial participation, then if it is 1 to 1 n relationship, it is some employees may not be working with any departments, that is the case. So that's why what should I do? In that case, better to capture it as a separate cross reference relation where I can have the employee ID and the department number, which is a foreign key pointing to this, this is pointing to the department number is a foreign key which will refer to the department number of the department table, and then employee ID is a foreign key pointing to employee ID, which is primary key of the employee table. This is how we can capture 1:n relationship into relational schema. Now let us see how to map m:(n) or n to m relationship types. Let us have a look at the theory behind that, or the guidelines or rules behind that. For each regular binary m:(n) relationship type R, create a new relation S to represent R. Include as foreign key attributes in S the primary keys of the relations that represent the participating entity types. Their combination will become the primary key of the new relation S. Also include any simple attributes of m:(n) relationship type as attributes of S. Let us take this example. It is a n to m relationship. I have employee entity type and then project entity type, and it is n on the employee side, m on the employee side. Either n or m, it indicates many. So that's why it says that every employee works with m number of projects, can work with m number of projects, and every project, each project can have n number of employees. And here I have indicated this as a partial participation. Okay, there is no problem, and the relationship is going to be works on, which indicates which that is forming an association between the employee entity type and the project entity type. And this works on relationship also has one specific attribute which is attached to the relationship, that is number of hours. It indicates that which employee has worked on which project for how many number of hours. And now coming to the mapping, this is a regular entity type, so this has been mapped into employee schema, relation schema, and this is a regular entity type and it has been mapped into project regular relation schema. Employee ID is the primary key and I have other attributes as fields of this relation, and then P&O is the primary key and then other attributes have become the fields of this relation schema. Then how to capture this n:(m) relationship? I can create a new relation called as works on. I can include the primary key of the employee table and primary key of the project table here as attributes, and the specific attributes which is attached to the relationship in the ER diagram is also made as the regular attribute of this relationship schema, relationship relation schema. This is called as a relationship relation because it is going to capture this particular relationship between employee and then project entity types. If you carefully observe, I cannot add, if I am not doing this, what are the other possibilities? I can add the P number as the foreign key in employee table, or I could add the employee ID as the foreign key in this project table. It is not correct because if I include here for any given employee, I can include only one project, project number P1 or something like that, which is not correct because same employee may be working on more than one project. That is why it is not possible to include P number as the foreign key to capture this association or relationship. Similarly, I cannot add the employee ID as the attribute and then make it foreign key pointing to this employee ID of the employee table because same project may have more than one employee working on that particular project. So both are not correct. So the alternative is what we have discussed, that is going to be the solution. Create a new relation and then include the primary keys of both the involving entity types, that is the relation schemas, and then make them as foreign keys pointing to corresponding tables, and then include whatever is the specific attribute which is attached or associated with the relationship as regular attribute of the relation schema. Now this will clearly tell that the data can be like this: employee 101 works with project P1 for 5 hours, 101 is also working with project number P2 and the number of hours is 10, 103 working with P1 and number of hours is 7, like this. That means, and here the employee ID alone cannot become primary key because multiple rows will have the same value. Here 2 rows have the 101 under employee ID column, and pnum cannot become the primary key because this row as well as this row has the same value under pnum column. So that's why the combination of employee ID and then p number is going to act like primary key for this particular table or relation schema. Of course, I have also attached the hours, which is a specific attribute for this relationship to capture the information about which employee has worked for how many hours on which project. So that information is captured in this. So same thing has been described in this slide, so nothing to worry about that. So please carefully go through the content of this slide, and which is going to tell you about the same thing what I have shown in the example. The next thing is how to map multi-valued attributes. For each multi-valued attribute A, create a new relation R. Okay, let us try to understand the concepts with an example. Okay, we are done with this, and then we discuss this now, that is how to map multi-valued attributes into relation as schemas. Let us take the example of employee entity type. Employee entity type here has employee ID, which is a key, employee name, age, and then there is an attribute called phone, and normally the simple and then single attributes, they will be represented like this with a single line oval, and if it is a double line border which indicates that it is a multi-valued attributes. That means the employee, for an employee you may need to store phone numbers, but there could be many phone numbers: home phone number, mobile phone number, office phone number, so on and so forth. So in that case I cannot, and this is a regular entity type, I have mapped this into a relation schema called employee, and then employee ID has become an attribute, employee name and then age, they have become attributes. Employee ID is the primary key, but I cannot add an attribute called as phone for this relation, because for a given employee 101, suppose he has one phone number and he may also have other phone numbers. So that's why it is difficult to capture that semantics in this representation. So that's why what is the solution? We need to create a separate table to capture the information about the multi-valued attribute. So that's why employee phone, that is the relation schema name I have created, and then employee ID is one attribute and then phone is another attribute. So this employee ID is a foreign key which will point to the employee ID of the employee table, and then phone is to capture the phone numbers for a given employee. For example, if you look at the data, 101 has phone number 4897 something like this, and 101 can also have one more name, one more phone, that is home phone, that is 56789 something like this. So and 102 can have something like this. So in this case what happens? Employee ID alone cannot become primary key because multiple rows have same value under the same column, and phone also cannot become primary key because multiple employees may have same office phone number, so that is not possible. So what is the primary key for this relation schema? The employee ID, which is a foreign key pointing to the employee ID primary key of the employee table, and phone, both are in combination, they act like a primary key for this table. So that's why both of them have been underlined. This is how we can map multi-valued attributes into relation schemas. Now let us see how to map n-array relationship types into relation schemas, and again we will try to understand these concepts whatever is contained in this slide with a real example. Okay, now we will see how to map n-array relationships into relation schemas. In this example, it is a ternary relationship because the number of different types of entity types that are involved in the relationship, that is supply, are 3. one is supplier, second one is part, and the third entity type is the project. So that is why it is a ternary relationship. And if you carefully observe, there is an attribute called SName which is a key for the supplier, part number is the key for part, and then project name is the key for the project entity type. And I also have a specific attribute which is attached or associated with the relationship supply, and this relationship is to capture which supplier has supplied what part to which project and what is the quantity. That is the information that is going to be captured in this relationship. Now, apart from these keys, let us assume that it also has other attributes. Each entity type, the owner, a strong entity type or regular entity type, has its own regular attributes. Let us assume that there are corresponding tables for capturing information about the supplier, this regular entity type, and for part you have this table, and then for project you have this table. Now, to capture the relationship, that is supply, this relationship can be captured using a reference relation, that is a relationship relation wherein I will include SName, project name, part number, which are foreign keys. This is a foreign key, this is also a foreign key, and then this is also a foreign key. This SName points to the supplier name of the supplier, and project name points to project name of the project table, and part name points to part number of the part table. And I have also included the attribute called quantity, which is a specific attribute of the relationship type, that is supply. And if you look at this, in this table I can store the information about the supplier S1 is supplying to project P2, and the part number is 10 and the quantity is 100 units, and S1 is also supplying to P3, the part number is 5 and then 700 units, like that. So it clearly, so what is the primary key for this table or the relation? Supplier name cannot become primary key because multiple rows can have same supplier name, and project name can also not, it cannot become the key, primary key, and part number also cannot become the primary key. So what can become the primary key? The combination of supplier name, project name and part number put together will act like a primary key for this particular relation schema or the table. This is how we can, and this example is for ternary relationship, and then similar kind of guidelines or rules can be used for mapping n-array relationships to relation schemas. Now let us see how to map class hierarchies. Class hierarchies means we have subclassing and then superclassing relationship between the entity types, then we need to map them into relations. And this we have seen in our ER diagrams, how to capture the specialization and then generalization in the form of subclassing and then superclassing. And that means I have a superclass entity type, and this is categorized or classified into two subclasses, and let us call it as A, and it is going to be X and Y. Now we call these classes as subclasses. This is going to be the superclass, and then the subclass entity types always inherit the attributes and relationships of its superclass. Apart from that, they can also have their specific attributes attached to them, and which have meaning only with those specific subclasses or classification. And we can have any number of classification based on different criteria for a given superclass. And if I have superclass defined first and then defining subclasses next, it is called as the specialization mechanism. And then if I have subclasses first and then find out the superclass by factoring out the common attributes from these two subclasses, it is called as the generalization mechanism. Now we will see how to map the superclassing and then subclassing concepts into relation schemas. We have two options. We are going to discuss about two options here. The first option is multiple relations for superclasses as well as subclasses, and the second option is multiple relations for subclass relations only. Yeah, let us have a look at this. In this example, this is the superclass entity type and these are the subclass entity types. In this example, it is about an employee. Employee has name, which is a complex attribute which has F name, middle initial and then L name, and it also has birth date and then address and then job type. Based on the job type, the employees are categorized into secretaries, technicians and then engineers. If an employee is a secretary and the specific attribute attached is the typing speed, and then if he is a technician, the specific attribute is going to be the technical grade, that is mechanical, fitter or turner, something like that. And then if he is an engineer, the engineering type, mechanical, civil, electrical, so on and so forth. Now, according to this subclassing, I have 3 subclasses and a superclass. The subclasses also inherit all the attributes of its superclasses, and then if at all a superclass entity type is involved in some relationship with some other entity type, in this example let us assume that there is a department entity type, this employee is associated with this department entity type, then all its subclasses will also enjoy that relationship. And now when we map this according to the first approach, we will have separate relations for superclass as well as subclasses. So that is why I will have a separate relation. This superclass entity type is mapped into a separate relation. I call it as an employee, where I had attached all the attributes, regular attributes, as the attributes or fields of the relation: SSN, birth date, address and then job type. Since name is a complex attribute, according to the rules what we have already seen in the previous slides, so pick the components, individual components of the complex attribute and then make them as the simple attributes or fields of the relation schema. So that is why the subcomponents of name, that is F name, middle initial and then last name, now have become the attributes, regular attributes of the relation employee. So this is the mapping of the superclass into a relation. Now we need to map the subclasses into relation schemas. For secretary subclass, I create this table or relation, and the specific attribute job typing speed is attached or included as an attribute, and then I also include the foreign key, an attribute which is a foreign key which will point to the SSN of the employee table, because every secretary is an employee. So definitely he will have all the attributes that are part of the superclass. And one important thing that need to be noted is the subclasses will not have independent existence. Every entity, if at all there is an entity available in the subclass, definitely it will have a corresponding entity in the superclass also. So that is why for every secretary entity in the subclass, there will be a corresponding entity in the superclass. That is why I have included the SSN as an attribute and then made it as a foreign key, and then which will point to the SSN of the employee table. And this is the key. This SSN is also working as primary key for the secretary table, and the specific attribute which is very special and specific to secretary subclass has been included as a regular attribute of this relation. Similarly, for technician also, the technical grade, which is a specific attribute here, this one has been included here as the field, and then SSN is a foreign key which will point to this. Similarly, for engineer, SSN and then engineering type, and this becomes the primary key, and this is pointing to the SSN of the superclass. This is the first approach. That means I have separate relations for superclass as well as subclass. In the second approach, what we can do is we will have subclasses, relations for subclasses alone. We will not talk about the superclass. That means if you look at this, vehicle is the superclass, and then car is a subclass, truck is a subclass, and then the superclass has some specific attributes, attributes which are common to car as well as truck, that is vehicle ID is common for both types of vehicles, price is also common, and license plate number is also common. And similarly, car has specific attributes, what is the maximum speed and then what is number of passengers it can carry. Similarly, truck has specific attributes, number of axles and then what is the tonnage it can handle. So that is why now according to the second approach, we do not have a relation for the superclass, but we have relations only for the subclasses. Now the car subclass entity type has been mapped into a relation called car, and here what I am including is I am including all the attributes that are part of the superclass as well as the specific subclass. So that is why I have vehicle ID and license plate number, price, maximum speed and the number of passengers. Of course, the vehicle ID becomes the primary key here, and then I have another relation for capturing the truck related data, and then here also I have license plate number, price, and then vehicle ID, and then number of axles has been added as the specific attributes. Of course, it will also contain the tonnage, which is the specific attribute of this subclass, and this is how we can capture the superclass and then subclass concepts that we see in ER diagrams into relation schemas. Now, the ER diagram what we have seen with respect to company database is shown here. I have regular entity employee, I have regular entity department, I have regular entity project, and then I have a weak entity type called as dependent. I have relationships, this one manages, works on, dependents of, so on and so forth. And if you carefully map this ER diagram into relation schemas using the rules what we have discussed so far in this lecture, then it is going to result in this kind of relation database schema. A relation database schema is nothing but a collection of relational schemas or details about the relations that the database contains. And if you carefully map, this is the regular entity has been mapped into a separate relation, department is also mapped into separate relation, project is mapped into separate relation, and dependent is a weak entity, it is a separate relation, and of course I have added another attribute called ESSN, which is a foreign key which will point to the primary key of the owner entity type, that is employee. And if you look at the works on, which is M:(n) relationship between employee and project, so I have included employee SSN and then P number, both are going to be foreign keys pointing to primary keys of the corresponding tables, and then ESSN and then P number put together is the primary key for the relation. And coming to department location, same department according to the, it is a multi-valued attribute, location, delocation is a multi-valued attribute for department entity type, so that is why I have captured it as a separate relation table. And I have included D number, which is a foreign key pointing to D number of the department table, and D location. One department may be located in many places, and D number and D location put together is going to act like the primary key for the table. And similarly, the D number, every employee has to work with at least one department and then maximum one department. I have included D number as a foreign key in employee table, and which is referring to D number of the department table. Similarly, every department will have a manager, so it is a foreign key here which is pointing to SSN here. And similarly, if you look at the unary relation supervision, and then every employee is supervised by one supervisor, so that is why this has been included as a foreign key which is pointing to the same relation SSN attribute. Then every project is controlled by a department, so that is why D number has been included as a foreign key which is pointing to D number of the department table. And whatever is the ER diagram that is given in the previous slide, here has been carefully mapped into relation schemas, or this particular ER diagram is going to represent the database which we are going to develop or design using high level concepts like entities, relationships and attributes, and the same thing has been mapped into a DBMS specific data model. Here it is going to be relational data model. So the same ER concepts have been mapped into relational schemas. This we call it as the company relational database schema. Okay, coming to the summary. In this lecture session, we have learnt the rules and guidelines that govern the mapping process from ER diagram to relational model. Given a ER diagram using certain rules, we can map the constructs in ER diagram into the relation schemas. Then we have seen rules for mapping entity types, both regular entities as well as the weak entities, and we have seen the rules for mapping the relationships, one-to-one relationships, one-to-n and then m-to-n relationships. We have also seen how to map multi-valued attributes into relation schemas. At the end, we have seen how to map the class hierarchies, that is, if our ER diagram contains the concepts like superclassing and subclassing, how to capture them into relation schemas. All these things we have discussed in this class. Thank you very much.